In this video, we are going to learn how to do double integrals using polar coordinates. So let's say that I'm given some region of integration R that looks like this. So here I'll have these two curves that are going to be given to me in polar coordinates. So in both of them, I'll have R isolated, and R will be equal to something on the other side that might have thetas in it. And there are some bounds for theta. So this region here is bounded by some theta value, which I'm calling alpha. And then it ends over here when theta equals beta. So one of the questions we might ask is like, when might we need to do something like this, like use polar coordinates? And the answer has to do with, there are some types of curves that are much simpler to write using polar coordinates. Like circles are just like r equals whatever the radius is in polar coordinates. That's way simpler than in our x and y, like x squared plus y squared equals something. So when I'm dealing with curves that are simpler to express in polar coordinates, that can make it better to use them. And then also sometimes my function just lends nicely to subbing in polar coordinates. Okay, so let's talk about how we do this. So my goal is to evaluate a double integral of some function over a region that looks like this. And I want to do this by using polar coordinates. And to do that, we will need to find dA in terms of polar coordinates. All right, so when I do this double integral, I'll have my function, and for the x and y, I'll sub in my formulas from polar coordinates. Like x is equal to r times cosine theta, and y is equal to r times sine theta. That's just what they equal in polar coordinates. But then what I need to know is, what is dA going to be equal to in terms of r and theta? So to answer that, I'm going to go to this picture here, and I'm going to slice my region into a bunch of tiny pieces. So I can get a sense of, what's the area of one of these tiny pieces going to be? And I'm going to call that delta A. So let me take this tiny piece here and then zoom in on it. So I'm going to draw a picture. I'll draw an arrow here. And we are slicing this region with a bunch of radial lines like this. And then a bunch of lines that kind of go around at the same constant radius. So same constant radius going a little further out, little further out. So because of that, this part of this shape is a curved line, some sort of curved line. These other two lines are straight. They are straight. They're outwards radial lines. They're straight. Okay, and then this line over here is also something curved. Okay, so this kind of looks like a rectangle, but it's not quite a rectangle. So what I'm going to notice is this length right here is actually an arc length of a circle. It's an arc length. So what does arc length equal? Well, to get the arc length, I need to know the radius of the circle. So if I draw this radius, I'm going to call that radius r. The other thing that I need to know is what's the angle that is swept across. So if I draw this other line and I look at this angle, I'm going to call that angle delta theta. And the arc length is the radius times that angle, delta theta. And we could check, for example, that if we had if we had made a full circle and looked at the arc length, well, the angle would have been 2 pi. So you'd get 2 pi times r, which is the full circumference of a circle. That checks out. Okay. So, and this other length that we've gone radially outwards, I'm going to call that delta r. That's how much this r, the radius, has changed. Okay. So this is not quite a rectangle, but it's pretty close. So I'm going to approximate this area using the area of a rectangle. Let's do that base, r times delta theta, times that height, delta r. And we can make this exact by using limits. And with limits, I get dA equals r. And then both of these terms become d something, d theta, and then dr. So this gives me a formula for what dA equals. dA is going to be r d theta, it'll be r times dr d theta. Okay, so what I'm missing now is my limits of integration. To get the limits of integration, we tend to put the dr on the inside for polar integrals and the d theta on the outside. So if I want to get the limits of integration in terms of r, what I need to do is, going back to my first picture, I'm going to draw an arrow radially outward. And think about, when does that arrow enter my region and where does it exit it? Because where it enters it, that's going to be my lower limit of integration. Where it exits, that's going to be the upper one. Okay, so in our formula here, the r values, the lower one is going to be r equals, this formula is h1 of theta, and then the upper one's r equals h2 of theta. Okay, and we got that by drawing an arrow radially outward from the origin, and the lower limit was where it enters r, and the upper limit is where it exits r, where it exits the region. For the limits of integration for theta, those are just based on the smallest and largest values of theta for that region. So what's the theta value here? What's the theta value there? Okay, so for my picture, that's the lower one is theta equals alpha, and the upper one is theta equals beta. Okay, and here I have a formula. We have a formula for how we're going to convert a double integral to polar coordinates. Okay, so let's do an example with this. Let us do an example. So this problem, we actually looked at this in our last section, but we didn't have a great way of evaluating it, and now we will. So it says, let R be a thin plate that consists of the part of this inequality that is in the second quadrant, i.e., it turns out this is a quarter circle. The density at any point on R is given by this formula. Find the mass of R. So let's begin by drawing a picture of my region R. So I can draw my axes. We can draw our axes. And I know that if we change this inequality to an equal sign, this is a circle of radius 4. But it tells me I just want the part of it that's in the second quadrant. So if I just draw the part of it in the second quadrant, I'd get this is 4, and this would be -4 on the x-axis. So then what does the inequality mean? That means not only are we looking at where the radius is 4, but also if it's less than 4. So we are going to end up shading in everything inside of this quarter circle as well. So that's what makes this a two-dimensional region rather than just on the curve. So I'm trying to find the mass. And the mass of a two-dimensional region like this is a double integral over the region, which I'll call R, my density function, rho, dA, because it's a double integral. So there are a few tip-offs here that I want to try switching this to polar. One is I have a circle bounding my region, and circles are so nice in polar coordinates. So a circle will always be R equals whatever the radius of that circle is, which in this case is 4. And that's the equation of the circle. That's just way simpler than x squared plus y squared equals 16. The other tip-off to switch to polar, so I am going to switch to polar, is that my function also becomes simpler if I plug in polar coordinates. Because I noticed that this is square root of 25. I can factor out a negative and then get x squared plus y squared. But in polar coordinates, x squared plus y squared, that's just equal to r squared. So when I switch to polar, I'm going to get a double integral. Let me give myself some space. And my density function becomes square root of 25 minus r squared. And we've seen that dA becomes r dr d theta. So I'll highlight that. The dA becomes r dr d theta. Now I need my limits of integration. So the inner integral is the dr. So I will draw an arrow radially outward. Radially outward from my region. And I think about when does it enter the region? But it enters it right away. So right away, that's when r equals 0. That's when it enters. And then where does it exit? Well, it exits on this curve, which I know that equation's r equals 4. So r equals 4. Okay. And then the outer limits based on theta. So what does theta go from? So over here, theta is pi over 2. That's where we start. And then where we end on this edge, it's pi. Theta equals pi. Nice. So it turns out that this function now, because this square root is getting multiplied by r, that's just way simpler to integrate than what I had before. Okay, so how can I do this double integral? Because this function is purely in terms of r, we can decouple the integral. We can split it up as the integral that has r's in it, which is from r equals 0 to r equals 4 of square root of 25 minus r squared times r, dr. Take that part and multiply it by the integral with everything with theta. So integral from theta equals pi over 2 to theta equals pi, we'd have d theta, and there's actually nothing here that has a theta in it, so technically there's a 1. Okay, so remember, I'm allowed to decouple it like that when these limits of integration are constants like this. And the function that I have here can be separated into something that is completely in terms of r and something that's completely in terms of theta. And having a constant fits that criteria. Okay, so now I got to do these two integrals. So the first one can be done with the u sub. We can let u be equal to 25 minus r squared. Then du would be negative 2r dr. If I isolate for dr, I'll get du over negative 2r equals dr. I also have to convert these limits of integration, because right now they're in terms of r. So I have r equals 0 and r equals 4. We got to plug those in to our u sub. So if I plug in 0, we get u equals 25. If I plug in 4, we get u equals 9. So doing the u sub, I'll get an integral where the 0 has now become 25. The 4 has now become u equals 9. I'll get the square root of u. The r is still there, and then the dr has become du over negative 2r. So this is nice because I can cancel the r's. I can factor out that 1/2. And ordinarily it'd be negative 1/2, but what I'm going to do to get rid of the negative is swap the order of the integral. So I'll put 9 at the bottom and 25 up top, and that switches the sign. And then square root of u is, well, u to the 1/2 du. And now I can do that antiderivative. I'll get 1/2 times, I add 1 to the power, I'll get u to the 3/2, and I divide by 3/2. But that's the same thing as multiplying by the reciprocal, 2/3. Okay, and then I got to plug in the 9 and the 25. I can cancel the 2's and I'll be left with 1/3, which I can factor out because it's a constant. And I'll get 25 to the 3/2, 25 to the 3/2, and then minus 9 to the 3/2. But when I have something to the to a fractional power, the power on the bottom, the number on the bottom means a root. So I'll have 1/3, and this means I'm doing a square root of 25. The number up top means do the power. So square root of 25, and then that's going to get cubed. Same thing for this next term. I'll do the square root of 9, but then that result has to get cubed. So I'll get 1/3, and this becomes 125 minus 27. 125 minus 27, which is 98 over 3. Okay, so the harder of the two integrals, which shouldn't be too bad, that's just a straightforward u sub. That first integral becomes 98 over 3, and that's going to multiply that second integral, but the integral of 1 is just theta. And then if I plug in pi and pi over 2 and subtract, I'll get pi minus pi over 2, which is just pi over 2. And then I can cancel the 2 from the top and the bottom. That leaves me with 49 pi over 3 for the mass. I just need the units. The units of mass in this problem were grams. And there we have it. We just worked out our first double integral using polar coordinates. So notice again that some of the key indicators to tripolar coordinates were my region, especially circular regions, lend really nicely to polar coordinates, just because the equations are much simpler in polar coordinates. The other reason was this function had this x squared plus y squared show up in it which just equals r squared in polar. And that's also just simpler.